Okay, let's continue. Now, some announcement. I try to organize my video clips. So from this point on, I changed the motion 1, 2, 3, 4 to part 6, and the previous clip will be part 5 with some momentum. And in the future, I will change on YouTube as well. So just let you know, and you were searching under my name and the Jackson State JSU Peter Chang or SCI 201. That's going to be the same. Okay. Now let's continue on the sensible heat. What's the definition for sensible heat? All right. It is defined the thermal energy required to change the temperature of a certain substances without changing its physical state. In other words, that energy is used for increase or decrease temperature of a certain amount of substances, 10 gram, 20 gram, 100 gram. But still within its same physical state as liquid or solid, does not have a physical state or phase change. That's what it is this way. Alright? So we already understand this, right? And then we come to the point, right? Now, is there any other heat involved the physical change without temperature, or with or without temperature change? Yes, we're going to get into that in the near future, right? That's a sensible heat. Now, what a sensible means, because temperature change can be measured or sensed with the instrument we call thermometer, right? So that is where the term sensible comes from, right? So now let's see if we are able to use the sensible heat to solve some problem about the amount of energy required to do the temperature change on certain substances, right? How much would it be? Let's pick up one problem on the pre-test already distributed to you a long time ago. And example is going to be pre-test number 31. All right, number 31. What is the statement? It says ask you to find out how much, right, heat will be involved. Now I use involved. That means it can be increase temperature, put energy in, or decrease temperature by taking the energy out of the substances. Not just evolve, right? That's involved. Will be involved when 500 milliliter of liquid water, right, is cooled. Now cooled means temperature goes down. Cooled down, right, from 25 degrees Celsius to 0 degree, icy water. Now put here icy means very cold. 0 degree. It's not ice, but icy, or icy water. So the solution would be, first, as we always do, a list of the knowns. A list of knowns. List of knowns. What do we were given, right? We were given the mass, right? The mass of water, right? Let's say, and it was a liquid, right? H2OL, liquid, and is what? Is 500 milliliter, and then multiply the density of the liquid water is 1 gram per milliliter, already specified in the previous video section. Should be arranged as part 5, right? So it's going to be 1 gram per milliliter. That's the density for water, right? And that gives us 500 grams. Now how this come up? This come up with the cancellation of milliliter to the milliliter, because one is on the numerator, the other one is the denominator. So we are able to cancel it into 1, and that 500 grams, right? Mass 500 grams, and then the temperature change. Now the T initial is going to be 25 degrees, correct? Is that 25? It's cooled down from, that's first, from 25 to 0. And the T final, let's put the same part of the board, is going to be 0 degree. So now, that's all the information we have, right? Of course, the specific heat capacity is known, 1 calorie per gram per degree. Now, I did not ask you to, I did not specify calculate thermal energy in what units. Now here we're just assuming in calorie, but we can also give you the both joule as we finish. Right, so what is the solution? We have to find the correct equation. The sensible heat, right here, equals what? The mass multiply specific heat capacity, right, and multiply the delta T, and we already did this. It's going to be mass times specific heat capacity times TF subtract TI, right? Now, according to that, then the mass is 500 grams. 500 grams. And the specific heat capacity for water, liquid water, icy water, or 25 room temperature, 25 degrees Celsius room temperature, you already learned in the chapter 1. All right, check my notes. The very first couple pages already there, right? Times specific heat capacity is what? 1 calorie per gram per degree. Both the denominator, right? And then you multiply what? T final subtract T initial. So the final 0. Watch it. So 0, right? The final subtract, right? Initials 25 degree Celsius, right? Outside. Now we first simplify before we do calculation. The gram cancel gram, right? We did already. Gram cancel gram, because one is in numerator, one is at the denominator position. They are able to be cancel each other, right? To end up with 1. You say, no, that's not. That's that's not numerator. That's denominator. No, it is the numerator. You can just make a fraction. Now you understand numerator. The denominator is 1. Right? 1. All right. Then if you have this cleared, then you are able to remember the fraction, multiply fraction. Then you find this G gram is on numerator, this on the denominator. So you got to cancel them, right? Same token to the temperature degrees Celsius, cancel the Celsius right here. All right. Now left over the calorie. That's all we need, right? So what is the final? The final will be 500 multiply 1 still 500 and multiply negative 25. Now how can we figure it out? We do this. Use mental math. not use calculator. Double it, become 1,000. Put the 30 behind 25, become 25,000, correct? Right? And then half it. So it's going to be what? 12,500. So the answer would be, should be, 12,500 calorie. Because everything is cancelled. That's the total amount of, and is that correct answer? Don't forget, here the negative sign. So this has to be negative. Right here, let's put negative, clear, negative. Now what does that mean? That means you have to take out 12,500 calorie of heat from this 500 milliliter of liquid icy water, the warm water, room temperature, in order to cool this much water down to 0 degree icy water. Alright? So that is amount to take out. So this process is negative sign, means we call the enthalpy. We say that is going to be the enthalpy for H, alright, and the heat, right? Change is going to be minus 12,500 calorie, and this negative sign means it's less than 0, right? Less than 0. It is considered as endothermic or exothermic. It's exothermic. It's exothermic process. You probably already learned exothermic, endothermic in your early year school, middle school, high school education, but we're going to get into this in detail very, very soon. Alright, so the answer is negative. Is that clear? Okay. So up to here, we can have something to repeat. Alright. Oh, by the way, if you want to know the energy in the scale of Joule, so it's easy to do that by multiply. So if you multiply 4.184 Joule per calorie, right? The calorie cancel calorie, then you have 4.184 multiplied 12,500 to give you a negative, don't forget negative sign, right? 52,300, right? Joule. Now, in my pre-test problem, I asked you to find or calculate the energy involved, right, for this process in terms of scientific notation, right? Scientific notation. Now, if you have to put in scientific notation, let's limit down to 3 stick figures. So what is the answer for scientific notation? So scientific notation would be negative, right? 3, 1, 2, 3. So it's going to be 52.3 stick figure, right? You don't put 0 behind the decimal point. That becomes a 5. And multiply, you move to the left. You did the operation, multiply 10 to the minus 3, and then you will have to compensate back by multiply 10 to the 3 to keep original value intact. So it is going to be 10 to the 3rd Joule. Alright, clear? That's a 2 right here. Okay. Alright. Now, this is the sensible heat in the exothermic process. And there are possibilities if I just switch the temperature change from high to low into low to high, then the value will be positive because the negative sign is coming from the temperature change. Either increase or decrease involve the opposite sign. Then the value of the heat or thermal energy with a sign indicates the process endothermic or exothermic. So imagine 25-degree warm water, right? One bottle, 500 milliliters, that's about 16.9 fluid ounce, right? Regular bottled water, right? And if you place the bottled water in the classroom for a while and then you equilibrize into the temperature of room temperature, 25 degrees, then you say, oh, that's warm water, I don't like drinking. I want to get cold, cool down, and cold water, and you put back in the refrigerator, and then normally the refrigerator on the vegetable section is kept around 0 degrees. So later on, the temperature of the water dropped to 0 degrees. That is how much heat will be taken out of that one bottle of water is from room temperature, and then the heat will be pumped out from the refrigerator through the compressor and the freon, and then carry out in the back of the refrigerator in the radiator to radiate into the kitchen. That's how much heat will be taken out for this bottled water. Of course, every dishes of leftover will do the same thing to get cooled and preserved for tomorrow, and then for later, and for your meal, and then but the heat is going to be pumped out from the refrigerator and then released into the kitchen. So what we asked the student to think one question in the past, say if you have a house, right? If you have a house and light is not on and there's no electrical device or appliance was running except the refrigerator, and then tell me where is the hottest spot in the entire house. Well, the hottest spot in the entire house in such a condition would be the back of your refrigerator, because the heat from whatever the food you store in there will be pumped out, going through an exothermic process, push the heat out of the refrigerator and then released into the kitchen, and then first out from the back of the refrigerator by the radiator. Okay, so that's the hottest spot. All right. Okay, now when we reach this point, we reach this term, exothermic, endothermic, and then next chapter actually, all right, this energy part, and we are going to get into something more detailed in the heat, including another situation we call latent heat. All right, and but we probably should get latent heat right now before we get into the energy and the thermodynamics part of chapter 4. All right, so let's introduce the latent heat. So what is latent heat? Right? Let's give a definition. What's latent heat? Latent heat is kind of opposite from the sensible heat. If we understand what the definition of sensible heat, right? The heat required energy to change the temperature of the substance without changing its physical state. Then the latent heat, I say, is opposite. Then it should be the thermal energy required to change the physical state of the substances without what? Without changing its temperature. Because the temperature doesn't change, so then it's not sensible. Right? Now what is the situation of this kind? Now imagine, right? Imagine this happens. You take one piece of ice cube, right? Ice cube from the freezer, not the refrigerator, food section, the vegetable section, but the frozen section, right? For the meat. And the ice maker, you pick up one piece of ice and place that piece of ice cube, right? And into the palm. Now wait. If you wait for a while, what happens? You see the ice starts to get melted, right? And the melted ice become icy water. There's a pool of icy water around the smaller and the smaller and the smaller ice, and then what do you feel from your palm? Your palm feels cold. So what happens? So if you have a thermometer at this moment, a very good thermometer, mercury thermometer supposedly, and you put the tip of a mercury thermometer, the tip of mercury, sticking to the icy water in the palm, in the middle of your palm, and then bury it there, and then wait for 30 seconds. You see temperature is going to be around 0 degree, right? And you say, well, it's next to my palm. My body temperature is 37 Celsius or 98.6 Fahrenheit, right? Water temperature is still at 0, doesn't increase much. Will increase if you keep on your palm until the whole ice melt, and then still you have time to hold it, and then of course eventually the icy water will warm up and become the regular room temperature water. But that's not the case here. We are talking about a very short period of time. You stick your thermometer in there, the thermometer will indicate the temperature of icy water is going to be 0. And if you touch the ice, it doesn't change at all. It's still 0 because the ice normally formed, the icy water froze right into ice at 0 degrees. So basically, the icy water and the solid ice coexist at 0 degree temperature. But how can this ice, solid ice, gets melted? Well, who does the job? Where the energy come to do the work to melt ice, melt water molecule one by one from the ice into liquid water, right? Well, that's energy from your palm, because you have a feeling of cold feeling in the middle of your palm. What does that mean? That means your palm start to lose heat, right? So getting cold, right? To your palm is going through an exothermic process, but for the ice is going through an endothermic process. Absorb the heat from your palm to get ice melted into icy water, because the energy getting to the ice crystal, which is the solid, right? And then shake down the water molecule and from the crystalline structure, and then getting to random arranged liquid. That's how the solid melt into the liquid water. So that is energy. But since you put thermometer, doesn't show the change of temperature change, right? There's no temperature change indicated or sensed by the thermometer. So it doesn't seem to be sensible easily, unless you know that. So the latent heat was not discovered very early, just like the temperature change. But finally we recognize there must be energy involved. That energy is not very easy to spot out, to discover, to observe. So we call them latent heat, which is hidden, which means hidden. The hidden heat. But that heat is required for changing the physical states for substances, and the amount is quite huge. So we're going to list its amount here. So latent heat, right? So for instance, for the let me erase a little bit. Right. Time left, 5 minutes. Because the latent heat only involve the physical state change at a certain temperature. So temperature is not changed. So it says without changing its temperature. Without changing its temperature, right? So the value, we're not going to give you a complicated table. We do not want to get involved very complicated compounds or substances. We stick to the smallest possible, simplest possible substances, and to explain the whole situation, which we are going to use water, right? Water. All right. So the latent heats, because you have two different kinds. For compound H2O, right? H2O. Now at 0 degrees Celsius, right? The H2O, right? Liquid, right? Water, which is water, can be frozen into H2O solid, right? That's called ice, right? And here is icy water, and solid ice, and it can go back, melt from solid ice back to liquid water. That's at 0 degree. Now, what's the value for this? It's a value with a double signs. All right. The value is positive, negative, 80 calorie per gram. Now, seems like we familiar with this kind of unit, but if you look deeper, something seems to be missing. For the specific heat capacity is calorie per gram per degree. You tell me why the degree sign is missing. Well, if you cannot figure it out, go back to review the definition of latent heat. We are talking about latent heats, right? That's one of them. All right, that's the latent heat as well. Without changing its temperature. So temperature is not changed. Why we need a temperature sign down there? Of course we don't need a sign of temperature symbol, right? So there's no temperature symbol involved. That's number one. And at 100 degree, right? At 100 degree, all right, the liquid water. Now that's when we're going down the temperature, but that's at 0 degree. That's where these two are put on there, coexist. And the water can be evaporized into gas steam, right? So that's a steam. That's a liquid water. Right? At 100 degrees, it's going to be liquid water. It's not icy water. It's boiling water, right? It's boiling water. Boiling liquid water, right? And also the steam can be condensed back to boiling water at 100 degrees. So they are also, the steam and boiling water coexist. The amount of energy involved, the latent heat for this kind of a transition of physical state, even bigger than that, it's huge, it's huge. So it is what? Positive, negative, almost 540 calorie per gram. Again, no temperature sign because temperature change is not involved. Now, at this temperature, right, the liquid and gas phases, right? Gas phases. Liquid and gas coexist. Yes. Now, here is the liquid and solid H2O coexist. Alright? That's a temperature change, the physical state change temperature, and we call freezing point. That's the boiling point. Or sometimes called melting point, and this is boiling point temperature. Now time's up. We continue next section. All right.